Hello, everyone. It's great to be here at JCON. Because of the way this talk is structured, I can see your questions while I speak. So just write them into the chat and I'll answer everything at the end of the talk. So let's get started. Again, I'm Shai Almog, and 25 years ago, I got lucky. I was sure I was this great programmer, a gift to programmer kind. Then I had a debugging session with a senior developer, and I was completely floored. All my confidence went completely away. And the way he wielded the debugger, he used these features and techniques that I was totally unaware of. I had no idea. We don't learn debugging in university because they don't teach, they can't test that kind of knowledge. They can teach it, but they can't test it. A tool we spend so much time inside on our day-to-day job is essentially left as sort of a home exercise that we need to learn on our own. I was lucky to get a glimpse at my ignorance, which made me study this tool and the surrounding process. Hopefully, I can pass around some of that luck onto you with this session today. But first, a few things about me. I was a consultant for over a decade. I worked at Sun, founded a couple of companies, wrote a couple of books, wrote a lot of open source code, and currently work as a developer advocate for Lightroom. My email and Twitter accounts are listed here, so feel free to write to me. Two things in my resume I do want to focus on a bit. First was the fact that I built JVMs both at Sun and independently in the open source. I also built a debug protocol implementation and a distributed debugger. So even with all this background, I didn't know all of the things in this presentation before I started blogging on this subject. So bear with me. I guarantee I will cover stuff that you don't know unless you follow my work online. I'm also busy writing a couple of new books, the first of which is getting really close to completion. It's a book about debugging. Follow me online to get notified when you can purchase it. This talk covers a small portion from only a couple of chapters, so not even the whole chapters. So there's a lot of additional material in that book, and I just signed the deal to do the second book today, so it's still a bit far off, but follow me and hear about that when it comes out. So let's get started. This talk is divided into 4 acts, and in the first one, which we already started, I'll do a bit of a warm-up because hopefully you all know the basics of what debugging is. So I assume everyone here knows how to set a breakpoint, step over it, look at a watch expression, even conditional breakpoints. I assume you know these things, that they're relatively simple. So I won't really cover them. I'll cover the more advanced things. This talk goes deeper than that. But first, I want to start with a 3-minute rant about a pet peeve of mine. It's short, and then we'll get to the technical stuff, I promise. It's just something I'm personally very passionate about. And it's why do people hate debugging? There's this sort of antagonism towards debugging and debuggers. In some cases, that makes sense. I used to debug on embedded and mobile devices, and back in the day, that was a terrible, terrible experience. I think the reason is that we feel stupid when we find that bug. Because bugs tend to be stupid. In most cases, it's something stupid the debugger shows us and we feel like idiots. No one likes to feel like an idiot. And the debugger is going there and sort of pointing at us, and most people feel that the debugger is doing that. It's Nelson. And, you know, I say there's a universal gesture for debugging, and it's this, the facepalm. Because that's really how we feel when we work with the debugger. We feel like idiots, and it's universal. Everyone does. After 30 plus 40 years of development, you still feel like an idiot when debugging, and that's okay, because I think it's Zen. It's a way to humble ourselves. People tell us all the time how smart we are all when doing the type of work that we do. I'm sure everyone here listening is probably familiar with that experience from their non-technical friends or even their technical colleagues, if they're lucky enough to have good friends as technical colleagues. This is a sort of grounding experience to know that we're all idiots in a similar way. So I'm thankful for debugging sessions, and I really appreciate them, and I think of them as a sort of meditation. And I think that if managers spend more time debugging, we'll all be happier. The managers will be happier, we'll be happier, because they will be more grounded and appreciate our work more. And we'll stop complaining about schedules to the same degree that they normally do. So that's just my 2 cents about that. So if someone complains about debugging, I hope you'll take that as an inspiration. But let's go into concrete debugging examples, specifically about control flow. We'll cover lots of features very quickly. Hopefully you know some you might, some not. Force return lets us return immediately from a method and potentially return a different result from the method. So when we're experiencing a problem, we can return fake data from a specific method to simulate a problematic condition. Unlike step out, we return from this point while skipping the rest of the method. We type in the return value, and the rest of the code won't execute. This lets us change the control flow of the app. We can return different results or skip problematic codes to see what happens next. Imagine a case of a hard-to-reproduce bug. This means we can simulate the conditions that can trigger that bug without repercussions. Next is jump to cursor. And this is one of my favorites here, not the favorite, but definitely close. We can actually move the current instruction pointer to a different position in the method. In IntelliJ, we need to install the jump to line plugin for this to work. This is an amazing feature and remarkably underutilized. I know people don't know about this feature because the install numbers for this plugin are sadly very low. Once the plugin is installed, we can drag the arrow on the left to bring the execution to a new location. If you saw a bug, just drag the execution back and reproduce it. We can skip over code that's failing, etc. Imagine building a unit test. Just drag the execution point back and forth and tune the variable values that you passed into the method. That way you can get a sense of the right arguments you need to pass to get good coverage. It's the ultimate do-over button, and you don't need to stop, recompile, or anything like that. It's an essential feature that so few people have. Out of 3 million installs of IntelliJ, I think it's 40,000 installs of this plugin, and that's the numbers too far away from one another. A watch point is a breakpoint that can place on a field. This is pretty standard, but a surprising number of people aren't aware that you can do this. We can place a watch point on a field which will stop every time the value of the field changes. This is a remarkably cool way to catch a case where some code mutates a variable. We can tune it to stop not just for changes to the field, but also for reading the value of the field. So you can really customize this. And this plays into the next feature, which is one of the most important ones I'm going to discuss today, which is trace points. It's probably the most important feature of a debugger that developers don't know about. Thanks to Visual Studio Code, actually, it got some visibility. In IntelliJ, it's still a bit hidden, but VS Code made it more visible. In VS Code, it's called a log point, not a trace point. They're a special type of breakpoint that doesn't break. They don't stop the execution and just log to the console. You can add a trace point by shift-clicking on the gutter. Notice I can write any valid expression here, either a string, variable, or method invocation. This is effectively a log I can add in runtime without restarting my app. It has full access to variables and everything. It's sprint line debugging without the risk of accidentally committing the debugging code to Git. That's fantastic. Notice that you can also set a trace point by unchecking the suspend checkbox you see here. A breakpoint breaks by default, which means all threads are suspended. A trace point lets you disable that behavior. Notice you can also create a breakpoint that only suspends a single thread and not all of them. That's a different subject, but it's really cool as well. Logging is debugging, and trace points are exactly that. If you have race conditions, which are normally very hard to debug with regular breakpoints, a trace point is a perfect tool to track those. Method breakpoints are similar to what we think of as line breakpoints, but they have some serious important distinctions. Method breakpoints are normally emulated by the IDE. It just uses line breakpoints to simulate method breakpoints. But there is a huge use case for real method breakpoints. Say we want to break on all the methods starting with the letters I and S in classes whose name starts with prime. This might seem far-fetched, but is actually a useful use case. If you have an abstract base class, subclasses follow a naming convention and they have many related methods, you want to track everything. You can do that using this approach. Notice you can also use trace points here and get very deep logging, such as a log or a stack trace every time a specific set of APIs is invoked. Breaking on all exceptions or on some problematic exceptions is terrible. The IDE stops every second. I'll enable breaking on any exceptions to show you this. People don't do that, and the reason is we hit a lot of exceptions. It becomes useless for real-life applications like this. We can solve this with a catch class filter. We can just exclude all the exceptions caught by the Java APIs, and this filters out these exceptions that are handled in the JDK. Exceptions in my application will still stop there. It's amazing that this isn't the IDE default. Without it, the feature of stopping on all exceptions is effectively useless. Next, we'll discuss debugging of asynchronous code. One of the reasons I love Java is that it is so darn easy to debug. We just step into a method and we can move between threads. That's easy. But some of that is habit. In recent years, the approach of using async await and similar asynchronous techniques gained traction, even in the Java realm. Debuggers kept up with this and let us see glued together stack traces. Let's dig deeper. Here we have a standard async example from JetBrains that uses a list of tasks and just sends them to the executor to perform on a separate thread. Each task sleeps and prints a random number. Nothing to write home about. As far as demos goes, this is pretty trivial. Here's where things get interesting. As you can see, there's a line that separates the async stack from the current stack on the top. The IDE detects the invocation of a separate thread and kept the stack trace on the side. It kept it in memory. Then, when it needed the information, it took the stack trace from before and glued it to the bottom. The lower part of the stack trace is from the main thread, and the top portion is from the executor thread. Notice that this works seamlessly with swing, with executors, with string async annotations, etc. This is very cool. So how does this work under the hood, and what do you do if you have custom code that's asynchronous? The IDE works by saving the stack trace in places where we know an asynchronous operation is happening, and then placing it later on when it's needed. So how does it connect the right traces? It uses variable values. In this demo, I created a simple listener interface. You'll notice it has no asynchronous elements in the stack trace. By adding the async schedule and async executor annotations, I can determine the point where an async code might launch, which is the schedule marker. I can place it on a variable to indicate the variable I want to use to look up the right stack trace. I do the same thing with the execute and get custom async stack traces. I can put the annotation on a method and the current object will be used instead. Seeing the values and the current state of what we're doing is one of the most important tasks of the debugger. In this second session, third section, we'll try to get deeper insight into the current state. One of the most annoying things to me is when I return from a method and have no idea what was the return value. This can happen because the developer didn't define a variable and just use the return value as an argument to an internal API, which I can't step into, or even used it as part of an equation. This feature solves that problem, and amazingly, it's off by default, because this is a very common problem. Luckily, the IDE has an option called show method return value, and it saves that value for us, so we can inspect it right away. Once I check it, you can see the return value is prime appearing in the watch area. Let's zoom in a bit. Right here is the fully qualified name of the method we returned and the value returned from that method. This is really useful. If there's one killer feature you will get from this talk, it's this. This, as I said before, I mentioned favorability ratings to features. This is my favorite feature in this whole session. If you're not floored by it, you either didn't understand it, or you're a cruel person. That's my only other explanation. This is my favorite feature. Object marking. It's also one of the harder concepts to grasp in my talk. Object marking lets us declare a new static variable in runtime and store the value of an expression into it without restarting or recompiling the code. To explain object marking, let's add a watch of the current thread method. We right-click the watch entry and create a marker object. Object marking lets us give a global name to a specific object, so we can later use that name even when the object isn't in scope. That means I can later check if the current thread is equal to the myThread variable and get the result I would expect. Notice that the IDE adds a debug label suffix to the name. Still, this is the exact same variable. This is immediately useful when dealing with many objects. In this case, I can literally check if the method will be hit with the same thread. I can use it to compare any objects instead of writing their pointers on a piece of paper, which is how we used to do things before this. I often use this with APIs like JPA, where we might sometimes have two object instances with the same identity, the same ID value, but different object instances. This is really hard to detect and hard to debug. With a tool like this, we can mark the object, one object, and then instantly see if we are getting a different instance in another method. There's so many bugs that you can solve with something like this. It's amazing. I used to love game cheats as a kid, and this specific feature makes me feel like it's a cheat mode in debugging. We can show all the objects of a given type. By right-clicking a thread and selecting Show Thread Objects, we can see all the thread objects in the virtual machine. We can even do that to string array and show all the string arrays in the VM. Notice that in both cases, we see internal objects from the VM. We even saw the JIT compiler thread. This is a remarkably useful feature, especially when tracking memory issues. This is something that was standing right in front of my eyes, and I didn't see it for ages. Filtering is a very powerful feature when we have code that views arrays or collection content. We can just filter the content using an expression and reduce the noise significantly. In this case, I have 4 elements in the pet clinic demo. I narrow them down by testing against the pet ID. Notice I used this to represent the current element in the list. This is very versatile. If we have a list of names, we can filter it so we can only see applicable names, etc. I used to work a lot with images and things like that with huge byte arrays, and suddenly, you run into a bug. Being able to filter the byte array data to see corrupt information or things like that is a huge benefit. And this is a feature that for some reason I didn't know about, and it's so useful. Streams in Java 8 are constructs inspired by functional programming that let us chain and process stream of elements. They're pretty cool, but one of the problems in them is that they are notoriously hard to debug. IntelliJ ships with a stream debugger that you can find in this button that I'm pointing at with the mouse. When you press it, you need to be positioned on a stream in the debugger. As you can see, I am in the line above. Notice that if you're not positioned on the stream, that button won't even show up. So you need to physically step over onto a stream. Pressing the button launches the stream debugger. On the top, you can see the stages of the stream expression. Notice that as I traverse through the stages of the expression, the objects change and draw a line between their original mapping and the new one. Initially, the list was of visits, and now we see the conversion to the pets in each visit. Since the final stage is a set, we will only get one instance of each pet. That isn't shown here because the relation is 1-to-1, but it is very visible in more complex and elaborate streams. The advantage here is that you can see the entire process in a single view that you can take back and forth, and unlike a loop, which you can normally debug by stepping in the debugger. The view here is a bit more complete and heavily inspired by time travel debugging and tools like that. Rendering is one of the features that most people just don't expect to exist, and this is one of the killer demos, especially if you do JPA programming. We think of watch expressions as a fixed thing, but when we're debugging a huge system, things can become tedious. A debugger can only show what it knows about, and for the most part, it's just guessing. With renderers, we can determine how an element is displayed in the watch, but we can go much further with renderers. To get started, we can customize the renderer through the right-click menu right here. For the most basic customizations, we can toggle and enable multiple features within this dialog. Then press apply to instantly see them in the variable view below. I can see the declared type of the field. We can include fully qualified names for class files. We can see the static field values. We can include hex values for primitives, which is a thing I always have on by default because I do lots of native and low-level stuff. And there's just so much more. But renderers slow down the program execution. So if you feel that step over is slow, we can just mute them like this. Then you can see individual values for renderers by clicking the specific item. Let's take this up a notch. We have a repository instance, and the visit repository variable below doesn't provide valuable information. We add a renderer that applies to JPA repository, which is the base interface of this instance. Then we just write the expression to represent the rendering here. We'll show the number of elements in the repository using the count method. Notice I don't provide an object instance. The IDE automatically runs in the context of the object. You can also use this to represent the rendered object. You can run this on demand, which makes sense for expensive operations. Look at the visit repository preview below and see the value instantly adapts to these changes. Now, if you're not familiar with repository objects because you're not a Spring developer, JPA repository objects represent essentially a set of entities, or saying that they represent a table is a bit inaccurate, but not too far away from the truth. So in this way, every time we look at the watch, we'll see at the number of elements that are in the table. the SQL table, and that's a much more valuable in terms of information than what we had there previously. Obviously, it's expensive. You don't want a count expression with every step over necessarily, but maybe you do. And the nice thing is you can use the more lazy version of this functionality to not do it over every step over, but make it a single click away, thanks to muting the render in this case. But this gets much, much better. The view repository is rendered with the right string containing the element count, but it isn't properly expandable. We can execute the find all method on expansion, and the responses will appear below the object like any other array. They will be filterable and everything. To make this even cooler, I can define an expression that indicates if the data is expandable using the count method. And this is the same as doing a select on the entire table when I press the plus to expand the variables below. Obviously, this is super, super expensive, and this isn't something that you might necessarily want to do for every JPA repository, but it can be very useful for local debugging because it shows you the actual data right in the IDE as you step over. And it might not be perfect for JPA, but it's amazing for every other thing. Imagine swing objects, which are very illegible by default. Imagine making them more readable as you step over them. And this is true for every type of object that we're talking about that's a bit verbose in terms of its internal state. Let's talk a bit more about custom rendering. You'll notice that everything looks exactly the same, the numbering, the lists of entities, etc. But when we open the list of renderers, it's blank. There are no renderers in this project. So how does this suddenly work without me defining a renderer? What's going on? There's another trick. We can use code annotations to represent a renderer. This way, you can commit the renderer to the project repository, and you don't need to configure individual IDE instances. This is pretty simple. We can add a dependency on the JetBrains annotation library into the POM. Notice this annotation library is just annotation, so it won't impact your runtime in any possible way and won't impact performance or anything. This is just annotations. We add an import to the renderer, and then we scroll down and we added a simple render annotation code. Notice that this is pretty much the code I typed in the dialog, but this time it's used in an annotation. So my entire team can benefit from improved view of the repository objects. Or if you're building a library for general consumption, you can, like that, make it more usable for everyone who's debugging your library. Every third party who steps over your code will suddenly see something beautiful in their watch area instead of seeing all of your internal state variables that might not be as interesting. So this is an amazing tool that you can offer users of any library, whether internal or external. When we think about memory debugging, we usually think about profilers, which do have some functionality for that. But the standard debugger has some amazing capabilities. Memory debugging is a very expensive tool, so it's off by default. When you don't need it, disable it so your debugging performance won't suffer. We start by launching the memory view from the IDE UI menu. Notice that the memory view is empty by default even after we launch it. This keeps the IDE responsive. In order to see the actual objects in RAM, we need to click the load link in the center. Once loaded, we can see the instance count for every object. This helps us get a sense of what exactly is taking up the RAM. But that's only part of the story. When we step over, there are allocations happening in the methods we invoke and possibly in other threads. We can see the difference between the current point and the one before when we look at the diff column. We can double-click an individual entry and see all the instances of the given object, which again is a remarkably powerful feature that we discussed before. But this is tedious. I have a fast machine with a lot of RAM. I can just enable update loaded classes on debugger stop, and I will no longer need to press load explicitly. Only do that if your machine is a monster. Track new instance lets us explicitly track the individual allocations that are going between 2 points. We can enable that by right-clicking any non-array object and enabling this option. Notice this is a really expensive option. I mean, if memory monitoring is expensive, this is expensive even for my machine. Once enabled, we see a small watch sign next to the tracked object, but there's a lot more involved as we continue the execution. I can now see only the objects allocated specifically in this diff and can understand exactly what happened in terms of RAM. I can also click an individual object and see the stack traces that triggered it all the way up to the literal call to new. So I can go back and see exactly which objects were allocated between 2 points in the code and who allocated them and which constructor they used. That's amazing when you want to track a memory leak, and usually the profiler just gives you the type of object that was allocated. This is the final mile. This is the part that tells you, okay, I want to look at that object and I want to see where that leak might have occurred. And this helps you track those things from the profiler. It's an amazing feature. Threading issues are notoriously hard to debug, but this reputation isn't always justified. Once you understand the basics, you'll find that most threading issues are pretty similar. Let's start with the basics of thread debugging. In the stack frame, we can look at all the current threads in the combo box above the stack frame. We can toggle the currently selected thread and see the stack for that thread and the thread status. Notice that here we chose to suspend all threads on this breakpoint. If the threads were running, we wouldn't be able to see their stack as it's constantly changing. We can enable the threads view in the right-hand side pull-down menu to see more. As you can see, viewing the stack is far more convenient in this state when working with many threads. Furthermore, we can customize this view even more by going into the customized thread view and enabling additional options. The thread group option is probably the most obvious change, as it arranges all the threads based on their groups and provides a pretty deep view of the hierarchy. Since most frameworks arrange their threads based on categories in a convenient group, this is often very useful when debugging many threads. Other than that, we can show additional information such as the file name, line numbers, class names, and argument types. I personally like showing everything, but this does create a somewhat noisy view that might not be as helpful. Now that we switched on the grouping, we can see the hierarchy of the threads. This mode is a bit of a double-edged sword, since you might miss out on an important thread in this case, but if you have a lot of threads in a specific group, it might be the only way you can possibly work. I think this way will be more common as projects like Loom, etc. come out and gain more traction. The first step of debugging a race condition is a method breakpoint. I know what I said about them, but in this case, I need it. Notice the return statement in this method includes a lot of code. If I place a breakpoint on the last line, it will happen before the code executes, and my coverage won't include that part. I only use it for the exit portion, because if I used it for both, I'd have no way to distinguish between exit and enter events. I make this a trace point by unchecking the suspend option, and then I log the name of the thread. I now do the exact same thing for a line breakpoint on the first line of the method. A line breakpoint is fine since entry to the method makes sense here. I change the label and make it also into a trace point instead of a breakpoint. Now we look at the console. I copy the name of the thread from the first printout in the console and add a condition to reduce the noise. If there's a race condition, there must be at least one other thread, right? So let's remove one thread to be sure. Going down the list, it's obvious that multiple threads enter the code. That means there's a risk of a race condition. Now, it means I need to read the logs and see if an enter for one thread happened before the exit of another thread. This is a bit of work, but it is doable. The next step is debugging deadlocks. Here we have two threads. Each is waiting on a monitor held by the other thread. This is a trivial deadlock, but debugging is trivial even for more complex cases. Notice the bottom two threads have a monitor status. This means they're waiting on a lock and can't continue until it's released. Typically, you'd see this in Java as a thread is waiting on a synchronized block. You can expand these threads and see what's going on and which monitor is held by each thread. If you're able to reproduce a deadlock or a race in the debugger, they are both simple to understand. Fixing might be a bit more challenging because thread safety is still a challenging thing, but understanding the problem and diagnosing the problem is often easier than people assume. Debugging doesn't matter at all. It's a tool. The one thing that really matters is production. And we can't use a debugger there. Or can we? The developer observability is an approach designed exactly for that. So when I talk about this, people instantly say, so why not use remote debugging? We have that. There are so many problems in remote debugging. First and foremost is the need to restart the process that we're debugging. We can potentially run with the debugger turned on by default always, but that is obviously a security risk. Then it's breakpoints. They break. I heard a story years ago about a guy who debugged a railed system and it literally fell into the ocean while he was stopped on a breakpoint because it didn't get the stop command. I don't know if that's an urban legend, but it's totally plausible. All remote debugging protocols are insecure, but I can personally attest about JDWP, which I'm familiar with. It's very insecure. In fact, there were CVEs already about products that left it open. It isn't designed with security in mind, but it's also a stability risk. How many times did a debug process crash on you? Imagine adding a breakpoint condition that's too expensive or incorrect. It might destroy your app in production. Just loading the variables in the watch can cause unforeseen problems in some cases, but this is the absolute worst. Say your app has a place where it takes user credentials for logging in. Maybe a third-party library you does that or something else. You can still place a breakpoint there and steal user login details. Worse, you can elevate permissions of your own user account because everything is writable. Just set a value of a variable and go ahead. This goes against privacy laws and is very damn likely. 60% of security breaches in organizations happen because of an employee. There's often a misconception of security that targets outside world only. This just isn't true. We'll start with logs, which are one of the more important features of developer observability. On the left side is IntelliJ, and on the right side, I have an application that counts the prime numbers running on a remote server. In this inside the side of the IDE, we can see the currently running agents, which are the server instances. We also see the tag above them. Tags let us apply an action to a group of server processes. If we have 1,000 servers, we can assign the tag production to 500 of them, and then perform an operation on all 500 by performing on a tag. A server can have multiple tag designations, such as East Coast, Ubuntu 20, Green, etc. Here I have only one tag and one server process. Another important aspect to notice is the fact that we don't see the actual server. As I mentioned before, this all goes through a management server. So production can be segregated behind a firewall, and I don't have direct access to the physical production server. I can add a new log by right-clicking a line and adding it. I ask it to log the value of the variable I, and will just print it to the application logs. This will fit in the order with the other logs. So if I have a log in the code, my added log will appear as if it was written in the code next to it. They will all get ingested into the service like Elastic seamlessly, or you can pipe them locally to the IDE. Notice I can include complex expressions like method invocations, etc. But Lightrun enforces them all to be read-only. But the thing I want to focus on is this. Notice the log took too much CPU, and Lightrun pauses logging for a bit, so it won't destroy the server performance. Logs are restored automatically a bit later when we're sure CPU isn't depleted. In fact, a common misconception is that logging is faster than system out. This is only true if you log to the file system or hide the log. System out is actually faster than logging to console. So to demonstrate this in a recent workshop, instead of adding a log, I just used system out to print the data. The benchmark took 3 minutes. When redirecting to file system, it took me 40 seconds. Lightrun logs to console took 25 seconds, thanks to suspension of logging. Logging is remarkably expensive in terms of performance, yet we print out redundant logs all the time because we might need it. With developer observability, we don't need such logs anymore, but there's so much more. Snapshots are breakpoints that don't break. Snapshots include the stack, the variable values, and all the stuff we need. We can use conditions on snapshots, logs, and metrics, just like we can on a regular debugger with conditional breakpoints. We can apply everything to a tag, which will place it in multiple servers at once. We can then inspect the resulting data like we would any breakpoint. We can click on methods and view variables. We can't step over, but our app will never get stuck. You know how you sometimes ask yourself is someone actually using this line of code? Yes, you can see the API endpoint is invoked, but it's hard to tell if the actual internal implementation code is reached. Countermetric is just that. You can use conditions to count things like how many people from a specific country reached a method. If you're thinking about deprecating a production API, this is the metric you need to keep your eye on. Notice that metrics are logged by default, but can be piped to statsd and Prometheus and visualized in Grafana. Locally, I often just grab the system current time into a variable and then offer a few lines or to log the number of milliseconds that passed to give me a sense of the overhead in the method. This is what a TikTok does, but at scale. We select a few lines, and then we can instantly see how much time is taken for the execution of these specific lines. Again, we can pipe everything and use conditions. An APM does something similar, but it's far more coarse, and this is very fine-grained in the code level. In closing, I'd like to review some of the things we discussed today. I hear people say, oh, I debug with prints and logs. To me, that sounds like the person is publicly declaring they don't know what's a trace point. So if you hear someone saying, oh, logging is the best type of debugger, then make sure they know what's a trace point. Memory debugging, field watch points, etc., can change your debugging like nothing else. Exception breakpoints can actually be useful with the right filters. Sometimes the only way to see that you got an exception is the console, and you might not just gloss over it since there was no alert. With this, you get an exception and the context variables. Use renders and similar tools to see variables you're working on. Use marker objects. Use all of these tools that are absolutely amazing. It will boost your productivity. Use observability tools like Lightrun to get deeper insight into your production environment. It's the most important thing we can do. And thank you for bearing with me. I hope you enjoyed this presentation. Please feel free to ask questions, and also feel free to write to me. Please follow me on social to keep up with my upcoming books. I already signed up to write the book after this one, as I mentioned. So there's a lot more coming up. Notice that this entire presentation, again, is based on a small subset of the first chapter of the book. and that is very vast in scope. And my DMs are also open on Twitter. Connect to me on LinkedIn, Twitter, all of the above. And I'd love to get your questions and chat. So let's see the questions here. Yeah, there is a you mean, have I written something down? There's a lot of stuff in my blog about pretty much everything I talked about here is in my blog. You can follow Debug Agent on Twitter, also debugagent.com, and there's a talk to the duck.dev where most of this appears, where pretty much everything I showed here today is there. And again, it will all be in the books. Renders are stored in the IDE. When you define them via the UI, they're stored in your IDE configuration. So you would need to do that every time you migrate your new computer, or unless you copy your details with you. And that's why it's very useful to add them in the code, as I mentioned before. If you add them in the code, you can share the love with all your teammates and help them learn about that. Yes, the heavy application. Debugging is often very slow. As I said in the presentation, I mentioned several things that are expensive in terms of debugging. And one of those things is renders. So try muting renders, try disabling and configuring various things within the debugger. So stepping over will feel more prompt. Again, ideally, you'd want a really powerful computer to debug something. So you can really, really make use of it. I'm using the most powerful computer I can buy because I need that extra hit to take to run with the debugger indeed. So if there are any more questions, again, would love to answer them online, and feel free to do that. And thank you all for coming, and thank you for the great feedback and questions.